Welcome back. We will resume with our lecture number 3 and we will talk about hydraulic fluid characteristics. And this will be covered into 2 lectures. When we talk about hydraulic fluids, we need to consider most important characteristics for any hydraulic fluid. And these are the pressure and flow. And before delving into these 2 characteristics, we need to keep in mind 2 statements, and we will understand these 2 statements later. The first one, force is determined by pressure and speed will be determined by flow. We will come to these 2 statements later. When we talk about the pressure is the basis of any hydraulic power, and a force applied on a surface area is called the pressure. If we recalled our previous studies, Pascal law states that a change in the pressure of an enclosed incompressible fluid is conveyed undimensioned to every part of the fluid and to the surface of its container. Hence, a static fluid in a closed vessel has the following characteristics according to Pascal law. Let's assume we have a piston and an incompressible fluid here, and we are applying a force by pushing the piston to below. So according to Pascal law, pressure works on a plane at right angle. Pressure is transmitted equally in all directions, and pressure applied on a part of a fluid is transmitted throughout the fluid equally. Everywhere I will be having the same pressure. The pressure can be expressed by the following formula, where P equal P equal force over area. P is the pressure and it is measured in Pascal or PSI. F, the force by Newton or pounds. A, the area where the force is being applied, which will be measured by meter square or inch square. And when we talk about the pressure, we need to consider 2 important factors. The first one will be the force multiplier and the pressure drop. When we talk about force multiplier, let's see an example or a sketch to give a better explanation. This sketch shows a force multiplier based on Pascal's law. The force multiplier is a closed vessel having different movable pistons, positions at each end. As you can see here, I have small piston and bigger piston. Both of them having different areas. And according to Pascal's law, the pressure everywhere in the vessel is equal, because it is an incompressible fluid in an enclosed vessel. So, P equal F1 over A1, which is also equal F2 over A2. Therefore, F2 will be equal F1 multiply A2 over A1, which is equal P. The force on the larger section area is multiplied by the ratio to the smaller area where F1 is applied. Let's demonstrate this by an example. Supposedly I have F1 is 40 kilonewton, and this force is applied to a piston of area 2 centimeters square. How much the other piston can hold a load where the A2 is 50 centimeters square? If we use the same formula where the pressure is everywhere equal, F2 equal F1 by A2 over A1, 40 by 50 over 2, which give me 1000 kilonewton. Therefore, a force of 40 kilonewton applied on a piston of 2 centimeter square area can hold the load of 1000 kilonewton subject to a piston area of 50 centimeter square. Simple as that. Now we'll talk about pressure drop. When fluid cross an orifice, if we can see here, the fluid is crossing an orifice or a restriction, it loses some of its energy. In this sketch, where the end is open, I have here an open end, you can find a reduced pressure at the downstream. Downstream of the orifice is this gauge, which shows a pressure drop or pressure less than the upstream pressure gauge. The difference between the upstream and the downstream pressure is called a pressure drop. This drop in pressure is caused by the flow and the restriction orifice. Hence, the magnitude of pressure drop will vary depending on some criteria. Number one, the rate of flow passing across the orifice or restriction. Second criteria, the size of the orifice itself or the restriction made on the fluid flow. The third criteria, the ease with which the fluid will flow, and this is the viscosity. Here in this sketch, the downstream now is closed. If you see here, the flow found a closed end. And the downstream flow must be the same as the upstream flow because there is nowhere for the fluid to escape. It suddenly faced a closed end. However, if the pressure in the fluid is lower, then the energy in the fluid is less. And as per the law of physics states, the energy cannot be destroyed. Therefore, the difference in energy must be given off in the form of heat. So, if the magnitude of pressure drop is dependent on the amount of flow passing the restriction, then it stands to a reason that there is no flow, where will not be any pressure drop. And it is obvious here, both gauges record the same reading. We can demonstrate another example. Suppose I have this sketch, and this is directly the relationship between the flow and the pressure drop is an important consideration in any hydraulics system. If there is no flow between point A and point B, there will be no pressure drop. Conversely, if there is no difference in the pressure between point A and B, there is no fluid flow between these 2 points. And here we'll come to the Bernoulli principles. Bernoulli principle tells us that the sum of the pressure and kinetic energy at various points in a system must be constant if the flow is constant. So, when a fluid flows through an area or areas of different diameters, as shown in this sketch, here I have 3 diameters where A and B is the same, however C is different diameter, there must be corresponding change in velocity. At the left section is large, so the velocity is low, and in the center the velocity must be increased because the area is smaller. It acts like a reducer. Again, at the right area, the area is increases to the original size and the velocity again decreases. Bernoulli proves that the pressure component at C must be less than at A and B because of the velocity is greater, and increase in velocity at C means an increase in a kinetic energy. Just imagine, speed, velocity, it will increase the kinetic energy. Kinetic energy can only increase if the pressure decreases. At B, the extra kinetic energy has been converted back to pressure and the flow decreases. If there is no friction loss, the pressure at B and A will be almost the same. This sketch will give us more clarity, and here it shows the combined effect of a friction and velocity change. Pressure drop from a maximum at C to 0 at B. At D, the velocity increase. If you see here, the area is reduced, so velocity increased, so the pressure head decreases. However, at E, the head increases as most of the kinetic energy is given up to pressure energy because of velocity decreased. We have here different sizes. If you see this area, now the area increased. Again at F, the head drops as the velocity increased due to area restriction. And finally, and according to Bernoulli principle, as the flow increases, pressure decreases. As the flow decreases, pressure increases. It is a matter of compensation. Now, summary of some key points for hydraulic principle. Hydraulic work done is a combination of pressure and flow over the time. So, pressure without flow results in no action, and flow without pressure also results in no action. Hydraulic pressure is the result of resistance to the flow and in force. So go back again, increase in flow, decrease in pressures, and decreases in flow will increase or will face or will find an increase in pressure. It was quite long lecture. Thank you and see you next lecture.